Right. Remember I said we were going to move back and we were going to look at how to predict the shapes of what a molecule actually looked like. Okay. So far we've been playing around and we've been saying, well, let's call them like this and whatever the case might be. But we actually need to just stop and have a look at the shapes, right? Now, there's a couple of possible shapes, and it's approached in many different ways, all right? I like the electron region approach, which makes a lot of sense, but let's just look at it from this point of view and say, right, let's take a simple one like CO2, right? Let's just get ourselves onto a black one. There we go. And let's get CO2. Well, what do? Right? We put the least electronegative, which is carbon in this case, in the center, right? And we know that carbon has got, remember, it's got the 4 joining places that it can bring electrons into, okay? Then we say, right, what does oxygen look like? Oxygen sits on this side, and oxygen has got over here, we know that it's got, tell you what, let's just change color. It makes it a lot easier, I think. Let's just say oxygen 2, 3, 4, 5, like that. Remember, oxygen had those 2 spaces on the outside. No? And along comes another oxygen on the other side over here, and it joins in, and let's just call that a green, shall we? So oxygen's got 1, 2, 3, 4, and I'm just completing the bonds on that side. Now, what happens in this situation? Well, we know that what we get is we've got to maintain the number of electrons. So, and we started off with 2, 4, 6, 12, 16. So we've got to keep 16 electrons. So these guys move up to here, okay? This one moves up, that moves up, and this chap moves, let's say, down to there, okay? So that we end up with double bonds this side and a double bond that side. Okay, so what have we got essentially at the end is we've got this situation here. Okay, we've got a C, double bond to an O, and we've got those on the outside. Okay, whoops, sorry, my bad. That's gone. And we've got this chap over here, this oxygen double bond at that side, and we've got those 2 electrons around there like that. Okay, so that has now formed its double bond. These 2 electrons can sort themselves out in space over there. On this side, remember, we've got 1, 2, 3, 4. We've got a double bond, right? So these guys occupy the space around, and we get a linear model, right? It means it's in a straight line, okay? That's as simple as that, because these guys have got space to sort themselves out into the empty space. Let's just look at it in that context and say, yep, this can move around, that can move, so we can get ourselves sorted out. Because remember, at the essence of, the core essence of this is the fact that we don't want the electrons, or the electrons don't want to be close together. They want to be as far apart as they possibly can in their space. Okay, remember, they occupy their space. The 2 of them in this case, the lone pairs, these here are our lone pairs, aren't they? Okay, because the lone pair, let's think of the lone pair as the electrons that come with that atom. Okay, so the lone pairs are that one and that one in this case. These are the ones that have got 2 separate parking spots that we can bring other electrons in. These 2 over here are part and parcel of the original atom. Okay, so we've got a linear molecule over there. Okay, now that's quite straightforward, and it's not too difficult a concept to work with, and generally speaking they sort themselves out. Okay, let's have a look and see what would happen now if I've got, this is our 2 electron regions, right? Okay, over here, all right, because we've got 2 electrons bonding, haven't we? Okay, now obviously a single electron is HCl, right? That's obviously going to be a linear molecule as well, or linear. So let us just have a look at saying, let's now have a look at what if we've got 3. Now most of the textbooks that you see, they use boron. Now if you look at boron, okay, on the periodic table, there's a reason that boron does what it does. Okay, remember in the dative covalent, there's an electron deficiency point around boron, aluminium, gallium, indium, all of those. there is an electron deficiency point. So it is prone to doing coordinate bonding, right? Now, let's just have a look at what the boron, okay? The boron, now remember, the boron, originally we started off with, we had a valency of -3. So our outer valence electrons were 1, 2, 3. Now, just to, can you see? This here is open, right? We've got 3 electrons. Carbon had the 4 around the outside, so they would sit over there. Here we've got 3, right? Now, what happens under this circumstance is we've got a fluorine comes along. Let's put in our fluorine. Here's an F over here. Here's an F over here. And we know there's an F over here. Let's fill in the structures of the fluorine. Well, we know that it has that, and the rest of it, all right, over there and there and there and there and there and there and there, is full. 2, 4, 6, 7, right? It's one short of a perfect octet structure. It's got a valency -1. The same thing's going to happen over here, right? And we've got like that, like that, like that, like that. So this electron has moved into that space, and we can complete it with this one over here. Can you see? That's going to move into that space there. So we're going to get those bonds. You can see that that has now formed a shape like that. Let's have a look using my lollipops over here. Okay. Now, let's take the central atom, the boron, there, right? Now, first of all, we've got 3 electrons that have paired in like that from the fluorine. These are my fluorine, and the green is the boron, right? So we've got our 3 over here. What happens now is, remember, this is an empty space down here, right? So these guys come and they share their electrons like that. But this is a big empty space. So what do you think these guys want to do? They say, there's a repulsion between them, isn't there? They say, well, hang on, we don't have to be so close. Let's align ourselves to be as far away from each other as possible. So what do we find? We find over here that these guys say, no, come on, move out the way. There's space down below here, right? There's space over here, plenty of it. So move around, shift around so that we eventually end up with an atom that is put around in space like that with an F over there and an F over there and an F over there, right? Now, in this situation, these guys are obviously going to go to 120 degrees like that, aren't they? Right? Because they're going to say, we can occupy this piece here, all right, this plane, this flat surface, we can occupy it much better, more efficiently than that, because we move ourselves around. So we end up with a shape that looks like that. And we give that a name. Right. It's called Trigonal planar. Trigonal, there we go, the 3 around the outside. Triangular on a plane. So let's think instead of trigonal, triangular on a plane. It's flat. So if it stood up, it would have the one here, one there, one there, and one there, right? And it would be in one plane like a wheel that it could move, right? Well, logically, the next one we have to say is, well, what happens if we get 4 electrons bonding into this, right? Well, 4 electrons, and the ones that normally get used is the PCl, no, not this PCl5, sorry, my bad, methane, CH4. We know that we've got methane. It's a very well-known substance. Okay. See, Kevin goes and writes a 4 there. Okay, H and H and H over there. We've got CH4, right? So once again, you'd think, well, okay, this is 90 degrees here, right? This is 4 electrons. Okay? It's a 4 electron situation that's moved, that we're bonding with now, right? Carbon is bonding with 4. Right, so now what happens? Well, that's great. Let's just take this and say, there we go. Fantastic. We've now got all of them in the same sort of plane. We say, but is that the most efficient way of doing it? Turns out not. Because they are now in a situation that says, but hold on, we've got more space. We are only sitting here in 3 dimensions, in 2. We are planar. But we can occupy the 3-dimensional space. So what do? They say, okay, you go up there, and now we'll all arrange ourselves around the thing in 3D. Okay? And what does that look like? Well, what it does is we've got a hydrogen, a carbon, and if you think about it, it forms a tripod there with one at the top. So we've got hydrogen there, a hydrogen over there, and over there. So we've got at the bottom here, like that, and we've got the 3 guys at the bottom, right? I need to get one of those polystyrene foam things because I'm going to have hands for this, like so. The 3 guys at the bottom and him at the top, like that, right? That's what she looks like that. And of course, this one sits in the middle, right? So we formed a tripod at the bottom because that's the most efficient there, and one on top. And they spread out equally, but they spread out in 3D now. That's what they're doing. Right? So when we get to the 4, we've now moved up to a 3-dimensional situation, right? CH4 is a typical one of those. Right. Now, what happens if we get 5, PCl5, for example, right? Okay. Well, we've got PCl5. Right? Just let me go back. This was the 4 electron. This is a 5 electron zone. Okay, because we're bonding 5 electrons. Well, essentially what we're going to get with this one, that one previously was the tetrahedral. Okay, its name is tetrahedral. Okay, it's a tetrahedron. It's got 4, as I say, the tripod at the bottom and the one at the top there. Okay, that's how we see those. Now let's look at the 5. Well, as you can imagine, it starts getting a little difficult to draw this now, right? Okay, so what we've got is the PCl5, okay, is called trigonal bipyramidal, right? Because we've got 5 electrons, right? Trigonal bipyramidal. Okay. Okay, and I'm sure if you look in your textbook, you'll see a much better drawing of it than I can possibly draw, or I can possibly represent with the lollipops I've got, because I don't have enough hands to do it. Okay, now, why? Well, what happens at the next level if you get 6 electrons bonding in? Okay, and luckily for us, okay, there's a shape for that guy as well. And it is normally where they go SF6, sulfur hexafluoride. What have we got here? We've got 6 fluorines. So let's put a sulfur, 1, 2, 3, 4, 5, 6. So we would think that we do this, right? Sorry, not FLs. Fluorine, F, the F, and another F there, and another F there. So it could form a central with 6 all the way around it, couldn't it? As a planar, okay? It's almost a hexagonal planar thing. But because we've got 3 dimensions, they spread out equally over or around the central sulfur molecule, right? So essentially what we end up with is and I'm sure once again you've got plenty of these in your books. We've got a molecule there, one there, one there, one there, right? And then we end up with one at the top here somewhere, all right, which sits above, over there, or rather let's do it that way, like that, over there, and then this one sort of comes down to there, to there, and to there. So we've got a molecule there, like so, and we've got the one sitting in the center, right, which is the molecule that we're bonded to. We're bonding 6. So we've got, say, a square there, right? These 4 are all around here, 1, 2, 3, 4, and then one on top and one at the bottom. So basically, we've got the 4 that sit over here like this, right? Okay, like that. We've got 4 that sit like that, okay? And then we've got the other 2, okay? the one sits up here and bonds through there, and the other one sits underneath the desk over there in the same position as that. Okay, so that's the way they're going to form together. You see it? And of course, our one in the middle sits over there, and these guys, remember this one is underneath, same position as that below it, right? So these are all then bonding in. Okay, now that sulfur hexafluoride forms what we call an octahedral structure, right? Octahedral shape. Okay, let me just go back up and put it underneath. This is octahedral shape, right? Now, that pretty much is the ones that we've got to know. But there comes a slight challenge in it, because now, now we have to look at a molecule. Like, let us take, for example, I just want to put this down on here, right? Let's take a molecule like a water, okay? H2O. Well, let's have a look at it. Well, we've got H2O. So let's put O over here. And in this case, we said we've got hydrogen here. Let's just draw oxygen structure. 1, 2, 3, 4, 5, 6. That's its outer valency shells, right? And we've got those two bonding in there. Now, what happens here, all right, is that we've got a situation where you would think that the hydrogen could come in there, and once again it would be planar, okay? In other words, it'll be straight, linear molecule, right, with the H. What actually happens is this, though. Okay, water, of course, has to be difficult, okay? It's the most amazing substance, actually, when you start examining it, and when you start looking at how lucky we are to have it. It's phenomenal, because the fact that water changes density when it freezes, ice floats, right? Imagine if ice didn't float. I digress for a second, but imagine if ice didn't float. Imagine if, like everything else, as it gets towards freezing, its density increases, it packs together, it would sink, wouldn't it? Like just about everything else we know. Well, imagine if ice did that. We wouldn't be existing, because the entire planet would freeze over from the bottom, wouldn't it? So the ice would, as the icebergs, they'd sink down, sink down, sink down, until we got basically a bed of ice at the bottom, and it just kept building up on top of that. So we'd be in a serious amount of trouble. Rivers, for example, we'd have no fish in them. The ones that freeze over, you know, where the trout in the winter love to go up, you know, and they freeze over, what happens? The river runs underneath that ice. So the entire fauna and flora of that river is preserved underneath a coating of ice. Okay, but if the ice was denser, it would fall to the bottom. Okay, I know I digress, but it's quite an interesting thought. So what happens with water is this: the oxygen, 1, 2, 3, 4, 5, 6. Okay, what actually happens, and that's how we draw it, right? We go around like that. The hydrogen comes in over here. Okay, in our water molecule. Okay. Remember, hydrogen can only have 2, right? That's its total, because it's only got a single S level, 1s2. So it can only put 2 around a hydrogen. Okay. Now let's have a look here. What have we got up top there? We've got a situation of we've got these 2 here. Okay. Once again, remember I said lone pairs. These 2 came with the oxygen atom, right? So when the oxygen atom was made, those 2 pairs of electrons on top, they came with it. The other 2 are the ones that are there sitting with a parking spot available. Now remember what we said about being polarities and things like that? What happens here is we know that if we take the change in electronegativity across these here, what happens? We have a situation like this, don't we? Let's just have a look. Here, remember we said electron time? Electron time. What do we mean? We said, the oxygen takes away the electron most of the time, but not all of the time. Okay? So most of the time, the electron sits here. However, a fair portion of the time, let's go back to the red, which is the electron swings down here, right? And ditto, the electron goes and makes a few loops around there. What happens there? It means that this top of this charge here, right, is, let us say, remember these are just numbers to help us understand, because the electron is 30% of the time out of its space, this can only be a minus 0.7. And this can only be a plus 0.7. Right? It's not always plus because the electron, the negative, is 30% of the time down there. So, but hang on, what are these two here? These two are full plus charges, aren't they? Let's just go and put them in. Okay? They are full plus charges. Always. Always full. If you like, what have we got here? We've got plus, there's 2 there. So we've got plus 2. And over here, we've got 1.7. 1.7, right? So let's just think of this as minus 1.7, minus 1.7. Do you see that? There's the minus 1, it's always there. This one, the red one, 70% of the time it's there, but 30% it's gone. So I can't call it a minus 2. I've got to call it a minus 1.7. So what do these guys do? They exert a force and they push this away. They say, hang on, you're not strong enough to sit here and keep us out the way. So they tend to force those electron pairs. They tend to force, here's our oxygen, here's our hydrogens, right? Now originally we said, well, we would think this, but that's not, it comes in at an angle, right? What do we have on top? Okay, now this is not another molecule. This is two electron pairs. Okay, it's 2 lobes of electrons sitting over there. Okay, these things are always full up. The purple ones are full up with electrons, so they are always there. These ones are not there, so these guys push them around and squeeze them around because they are the stronger charge. Remember, they try and stay as far away from each other as possible. So these guys push each other as far away as possible and squeeze these guys down. So the bond angle is distorted from what we originally thought it should be from just a diagrammatic point of view. That's the process of this lone pairs exerting forces on the others. Okay. Similarly, we've got the same thing if we go and we look at ammonia. You've got the same situation, right? Let's look at ammonia. Okay. We've got, let's move it up a little bit here so that I'm not in my own space. Okay. Okay, let's just go. We've got nitrogen, right? Now remember, we said nitrogen 1, 2, 3, 4. Just to recap, where is it? 1, 2, 3, 4, 5, 6. It's 7. So I've got to put 4, and I've got to put, how many have we got? We've got 3 short, aren't we? So there we go. What have we got? We've got nitrogen was 7. 1s2, right? 2s2, okay? That's 4, 3p3, okay? There we've got our 3, okay? 1, 2, 3, 4, 5, right? So we've got 5 electrons in our outer shell. 1, 2, 3, 4, 5, right? Now we know that nitrogen comes along with hydrogen, NH3. Remember, we've spoken about it. You're going to see a lot more of it. We're going to be doing a lot more of the NH3 structure, especially when we get to equilibrium chemistry. Okay, so what do we do here? Can you see up here? We've got a lone pair there, right? Now, this lone pair is going to force these guys around, right? And we've got a 3 bond, right? If we go back, let's have a look what happens to a 3 bond. All right, shall we? Right, let's see, where are we? Where are we? Okay, whoa, not there. There's a 4 electron bond. 3 electron bond, we've got a trigonal planar, was BF3, right? Now in this case, what do we get here? We say to ourselves, right, this chap over here is going to, this lone pair is here most of the time, so it is going to exert a force on these guys, and it's going to push them down. It's going to squish these two down over here like this, isn't it? Right? So our nitrogen is going to then, or rather our ammonia is going to be forced down by the lone pair on top. And Let's have a look what the bonding angle of that guy is, just for interest. Okay, water was, that was a perfect one. Let's have a look here. Water is, I think it's 104.5. Yes, water comes to 104.5 degrees, just for interest, right? The bond angle here, bond angle, okay, 104.5 degrees, okay? Okay, and it's an angular molecule, okay? It's angular with 104.5 degrees. The nitrogen, okay, is trigonal pyramidal, and it's 109 degrees. Okay. Okay, let's have a look here. And it is bond angle of 109 degrees. Okay, and it's trigonal, okay, pyramidal. Alright. Okay, so that kind of explains what is happening. It's the effect of the lone pair that sits on top, right? That's what's actually happening here. It's forcing these away from the central atom, and it's distorting the overall shape. It's forcing them down to occupy less space because they're not permanently there. And remember, for a coordinate bond or a dative covalent bond, it's exactly the same as a normal covalent bond, right? Treated exactly the same once it has formed. The electron sharing over there. Okay. Right, next what we're going to do is we're going to move along and start finishing off with some examples in this scenario, and putting something together that we can actually work with and we can calculate and get an understanding of it before we move on to, there's a section in between which is the inert gases, right? The noble gases as such, the gas structures, where we're going to be compressing gases, heating gases, cooling gases and things like that. That we have to do as the next section. Then we're moving on to the basis of it. We're going to put it all together and we're going to look at stoichiometry, right? So the gases are going to give us different things regarding standard temperature and pressure, and changing the pressures and temperatures and looking what happens to them. Okay.